In today's video, we will cover semiconductor materials. Semiconductors are used in the construction of transistors, diodes, and integrated circuits. So, to get a clear understanding of these devices, it's great to learn a bit more about semiconductor physics. Let's begin with the classification of materials based on their conductivity. We have materials that readily conduct electrical charges, aptly named conductors. Insulators that do not conduct electrical charges, and finally semiconductors that are somewhere in between. Materials such as silver, copper, gold, and aluminum are great conductors. The unit of electrical conductivity is Siemens per meter. Copper, for example, has an electrical conductivity of about 5.8 times 10 to the power of 7 Siemens per meter. Conversely, insulating materials such as wood, glass, or plastics have a low conductivity value. Dry wood, for example, has a conductivity of approximately 10 to the power of -14 Siemens per meter. Examples of semiconducting materials include silicon, germanium, and gallium arsenide. The conductivity of silicon is around 1000 Siemens per meter. This places it between what we would consider a good conductor and a good insulator. Now, let us look at silicon in detail. It is the most widely used semiconductor material in today's electronics. This is a representation of the atomic structure of silicon. It has an atomic number of 14, meaning that it has 14 protons and 14 electrons. We see that the electrons exist around 3 orbitals. Today, we are interested in the outermost orbital. It has 4 electrons. Another way of saying this is that silicon has 4 valence electrons. Without going into too much details, know that an atom wants its outermost orbital to be filled. In the case of the silicon atom, it requires 8 electrons to fill its outermost orbital. This can be accomplished by a silicon atom by sharing each one of its 4 valence electrons with each of 4 neighboring silicon atoms, forming single covalent bonds. This results in a strong, stable, tetrahedral structure, which gives crystalline silicon its characteristic properties, including its semiconductor behavior. How so? This is the cool part. At non-zero Kelvin temperatures, some of these electrons in the silicon lattice break away from their covalent bonds and move freely, giving the semiconductor some conductive properties. The number of free electrons is of course much less compared to conductors like metals. Now some terminology. The vacant spot in the covalent bond left by the electron is known as a hole. We think of an electron as having a negative charge. As such, we can imagine that the absence of electrons, aka holes, having positive charge. Keep this in mind as it will become important later. In a semiconductor, due to thermal activity, free electrons are continuously generated, and holes created. These electrons will eventually recombine with another hole in the material, and so on. This is basically how current travels along the semiconductor. Semiconductors can be classified in 2 categories: intrinsic and extrinsic semiconductors. When the semiconductor is made up of only one type of atoms with no impurities, it's known as an intrinsic semiconductor. The silicon semiconductor we saw previously is such an example. On the other hand, when external impurities or atoms are added to the crystalline lattice, it is known as an extrinsic semiconductor. This process of adding impurities is known as doping. Why is this done? Well, it is to influence the conductivity of the semiconductor. Now, depending on the type of impurity or dopant, the extrinsic semiconductors are classified into 2 types: p-type semiconductors and n-type semiconductors. Let's look at this in more detail. In the case of p-type semiconductors, we generally add trivalent atoms to the silicon lattice. Trivalent atoms, as the name implies, have 3 electrons in their outer valence shell. Examples of such materials include aluminium, boron, and gallium. Unlike the silicon atoms, which has 4 electrons in the outer shell, these elements only have 3. Which means that, where these atoms are introduced in the lattice structure, it creates a vacancy where the 4th electron of the silicon atom would have been. In other words, a hole is created. Therefore, when a semiconductor like silicon is doped with a dopant like this, it creates an excess of holes in the material. This is called a p-type semiconductor, with a tendency to accept free electrons more than a regular semiconductor. In the case of N-type semiconductors, the dopant is generally a pentavalent atom. It has 5 outer valence atoms compared to the 4 in silicon. Examples include arsenic, antimony, and phosphorus. When these atoms replace a silicon atom in the lattice structure, 4 of the 5 electrons are used to create the covalent bonds, leaving 1 extra free electron that is free to move around. This means that N-type semiconductors have an excess of electrons compared to normal intrinsic semiconductors. Now, when we apply a voltage across these semiconductors, something interesting happens. In p-type semiconductors, when an external voltage is applied, holes, which are positively charged, move towards the negatively charged end or the cathode, in the direction of the electric field. On the flip side, N-type semiconductors, with their extra electrons, allow the flow of electrons towards the anode when exposed to an external electric field, moving opposite to the direction of the field. In essence, the conventional current flow of positive charge appears to move from the p-type to the N-type semiconductor in a circuit. When we bring p-type and N-type semiconductors together to form a p-n junction, we create a fascinating platform that forms the basis of diodes, transistors, and numerous other semiconductor devices. We will dive into the details of the p-n junction in a future video. Thank you for sticking till the end. We hope you found some useful information here. Like and subscribe for future content from us.